That's a good start for bell work. 1, 2, 3. 3 problems, 3 different operations with the exponents, which we've seen already. So, well, nothing new on this stuff. Yeah, there we go. 1, 2, 3 answers. And this first one, you'd have to add those exponents to get the 9. On this one, with the separation of the parentheses, you'd have to multiply the 4 and 5 to get 20. And then 3, you're going to take the 5 and subtract the 4 because it's being divided the bases. So that's x to the power of 1. Just show it as x. Good. There's our objective for the day. I can find, simplify, and evaluate negative and zero exponents. Just take 30 seconds and write that down, please. All right, now we have seen an example of some negative exponents, I think. So if I remember right from that lesson, it showed b to the power of 3 over b to the power of 5. Now if we expand these, now that we're doing a lot of expansion, but you get 3b's in the numerator, 5b's in the denominator, and we know that anything divided by itself is a 1. So we make these phantom ones here, and what do we get? We get something over b now to the power of 2. And be careful, remember, this is not that they're canceled out, it's just that they become phantom ones, so they've been crossed out, but not canceled out. And yes, we need something to fill in the space for that numerator, just throw it away. And that would be one of those phantom ones there. So that's 1 over b to the power of 2. On the other hand, if we applied the rule to this one, we'd have the base b, because it's the same base, the two exponents 3 and 5, and it needs to be in this order, numerator and then denominator. Since we are dividing here, we need to subtract those exponents. So this ends up being b to the power of 3 minus 5 is negative 2. All right, so we're essentially saying that these two are the same. B to the power of negative 2 is exactly the same as 1 over b to the power of 2. Now, the way that I prefer that you look at this, although people have their different ways, is that this b to the power of negative 2, I would put it over 1 as a fraction. And what happens is, if you ever have a negative exponent, it doesn't matter if it's in the numerator or denominator, just flip it, and then the exponent will become positive. So on this one, where it starts, b to the power of negative 2 is in the numerator. If you flip it into the denominator, then the exponent becomes a positive. The base does not change, but the exponent will change its sign, okay? So this also means that if you saw something like this, let's say 1 over x to the power of negative 3, if you needed to make the exponent positive, you'd make it just x to the power of 3. So, and yeah, that does have a phantom 1 divide by 1 right there. So where it was in the denominator, it then flipped and went into the numerator to make the exponent positive. And again, one of the common errors that we find in this negative exponent stuff is where students start flipping the base and then making the base negative or positive. But it's not affecting the base, it's only affecting the exponent. So that's how the negative exponents will work. And I think we've talked about this already. If you ever see anything to the power of 0, it's 1. And the reason that is because the way you get an exponent of 0 is you'd have to take something and pretty much divide it by itself. It doesn't really matter what the exponents are. Like in this example, you take the base x, 4 minus 4, in the exponents would give you base x, but then an exponent of 0. And we already know, just kind of going backwards on this one, anything divided by itself is 1. So while those are kind of separated by the word, anything to the power of 0. It doesn't matter if these are decimals. It doesn't matter if they're negatives in parentheses. It doesn't matter if they're fractions in fraction. In this fraction, anything to the power of 0 is 1. And yes, we can talk about if the base is 0 later, but for now, this is all you really need to know. Even like this stuff right here, right? That's kind of what we just talked about, is like right here you got x to the power 5 over x to the power 5. We know anything divided by itself is 1. But, yeah, and if you expanded this, you'd get 1, 2, 3, 4, 5 x's in the numerator. And then you divide it by the same number of x's in the denominator, like this. And again, just like we've seen, anything divided by itself becomes these phantom ones. So this ends up, since everything was crossed out, you just need to show any of the phantom ones as a not phantom one. So that would be simplified as 1. But again, just going back to the rule, you take your base x, and then the two exponents, 5 and 5, you would subtract them because it's division to get x to the power of 0. So we're saying these are the same thing. X to the power of 0 is 1. And again, x is a variable, which means that it could be anything. It could be a fraction, it could be another letter, like y over y, or it could be an expression as well. It doesn't matter. Anything divided by itself is 1. So anything to the power of 0 is 1. All right, take 10 seconds and try these. 10 seconds, go. I actually prefer these. I love these kind of problems. Like, if I could just do these all day, I would actually be more happy than I probably should. But in any case, on this one, anything divided by itself, even if it's 4 to the power of 3 divided by 4 to the power of 3, boom, 1. Or down here, a times b, that's in parentheses, but it doesn't matter. It's to the power of 2. It's the same thing in the denominator. Anything divided by itself is 1. Or in this case, here we have a set of parentheses. We have a bunch of, well, garbage on the inside. But the main thing we need to notice on this is that it's an exponent of 0 right there, so it's 1. Okay? Now, the sooner you make that an instinct to see, oh, there's an exponent of 0, so whatever's on the inside of that parentheses or whatever it is as the base is 1, the better off you're going to be. Now, it may not be the full expression like we see on C. Like, sometimes they'll say, well, it's just x right here to the power of 0, and then you make that a 1. Again, the sooner you make that an instinct, well, at least the faster these problems will go. Make sure that we don't get that mixed up. Remember that an exponent of 0 does not mean multiplying by 0. It's just saying that, well, pretty much you have 0 of those bases, so it's like, well, what do you have left? It would be a phantom 1. So yeah, and it's not as common a mistake, but it does happen from time to time, especially while we're practicing on this early right now. It's like, well, this should be 0, right? No, it's an exponent of 0. It's very different, so be careful on those. For example, like on number 4 right here, you'd have a base 4. It's being divided, so we know we're subtracting these two exponents, 3 and 3. So it's the same as 4 to the power of, well, 0. Which is 1 right here, because if you actually evaluate this, you'd get 1. So that's why it's an exponent of 0, because it's really saying that you've taken something, in this case 4, and divided it by itself to get, well, 1. Right now, you guys are just trying to get used to seeing an exponent that's 0, whereas, and you can see that there's not really a huge difference between this and this, right? Like, well, it's just that the 0's smaller, and then in the top right corner, be careful with that, because its size and location will tell you the difference between multiplication of 0 and exponent of 0. It's very different. So we talked about the rule for this in the objective. That's okay. We're still gonna go over this stuff. Okay. So I'll expand these just once, and then I pretty much won't expand them ever again. So it's important that you understand how this rule works. But for this first example, I got 3 to the power of 3. That's 3 3's in the numerator. In the denominator, we've got 5 3's in the denominator. 1, 2, 3, 4, 5. And just like with the base B's example that we've seen already, well, those are crossed out as phantom 1s. And then, well, what are you left with? You got 3's in the denominator, 2 of them, so that's 3 to the power of 2. And again, don't forget to include that phantom 1 in the numerator. Otherwise, it just looks empty. And people may assume that it's 0, but it's really just a phantom 1. Be careful on that. Now, if we were to use the rule on this, though, you take the base 3, and then those two exponents of 3 and 5. And it needs to be in that order. It's always the numerator exponent, and then the denominator exponent. And yeah, since these are being divided, you subtract those exponents to get 3 to the power of 3 minus 5 is negative 2. So again, this is just indicating that if you have a negative exponent like this, and this would be considered a numerator, right? You'd say, well, that's 3 to the power of negative 2 over 1. All you got to do to change the exponent to a positive, because that's the way it's going to want it on the assignment. To change that to a positive, you're just going to change the location of the base. So now it's 3 to the power of negative 2 in the numerator, If you make it 3 to the power of 2 in the denominator, now the 2 exponent is positive. Once we start subtracting the exponents, it's possible to get negatives as long as you're subtracting something that's bigger than what you start with, like we see with this base 3 stuff. So where we took away 5 but only started with 3, yeah, we have to go into the negatives for that. But in reality, it's just showing, well, it'd be 1 over 3 to the power of 2, or 1 over 3 times 3. So yeah, they won't ask you to expand this, but if they did, you would just know that it's 1 over 3 times 3. All right, for this next one, just because I don't want to make this too redundant, I'm just going to use the rule. So see how there's a 4 in the numerator, so that's first. That's my first exponent. And then 7 in the denominator, that's my second exponent. Yes, these are being divided, so I'm going to subtract those exponents, which would then make this a to the power of 4 minus 7 is negative 3. Now, again, they're not going to want this with a negative exponent. So I would show this as a to the power of negative 3 over 1. And if I flipped that a to the power of negative 3, or just moved it to the denominator, then I would have a to the power of positive 3. But since I moved it to the denominator, I didn't really have anything in the numerator, so that's where we need that phantom 1 right there. Okay. So again, on the assignment, you may end up with negative exponents. For the most part, it's going to say we only want these as positive exponents. We'll just, instead of keeping it the way it is, just flip it. Okay. And again, you can flip it from denominator to numerator. As long as you're flipping it, then it will change the exponent. Now, just as a quick refresher on this, when we flip fractions, we call that reciprocation. So if you're going to reciprocate the expression, the fraction, then it's going to change the sign of the exponent. Just as a quick gimmick, some people say if it crosses the fraction line, then you change the sign. I don't know if that helps, but I threw it out there. All right, and we can see from now on here, like this one, I don't really want to expand 10 of these B's like on the next one. I don't really want to write out 50 of these A's. I know you guys want me to, but I'm just not going to. So I'm going to focus on each of the bases separately, and we'll stay with the rule. So on this first one, I get, just with base A's, I got exponents of 3 and 6. 3 in the numerator, 6 in the denominator. This is being divided, so I need to subtract those exponents. That will then make a new exponent for base A. 3 minus 6 is negative 3. Now again, we don't really want this as a negative exponent. So, since that would be considered a numerator, I would then flip it into the denominator, which would then make the exponent positive. Now that's just the base A. We still have the base B to work with as well. Base B has exponents of 6 from the numerator, 10 from the denominator, and again, those bases are being divided, so I would subtract those exponents. So that would give me base B to the power of 6 minus 10, which is negative 4. Again, I show it as a fraction so that I know where I'm flipping it to. This is going from the numerator to the denominator, which in turn will change the sign of the exponent. So now it's B to the power of positive 4, but in the denominator. Well, what goes in the numerator is just a phantom 1. So again, we see the practicality of this because no one really wants to write out 50 A's. I suppose some people do, but not very many anyways. So let's stick with our bases. We got bases of 4 and A on this. I'm just going to start by working with the base 4. So base 4 has an exponent of 15 in the numerator. So that's first exponent, and then 20 from the denominator. That's my second exponent. This is all being divided, so we're subtracting these exponents. So that would give me base 4 to the power of 15 minus 20, which is negative 5. So once again, I'll show that as a fraction as over 1. And that will give me, it'll allow me to change or flip that base 4 from the numerator to the denominator, which now instead of an exponent of negative 5 becomes positive 5, okay? And then we'll focus on the base A, which has 30 as its exponent in the numerator, 50 as the exponent for the denominator, and again we are subtracting these. So 30 minus 50, will give me base a to the power of negative 20. But again, I'm just going to flip that because it would be considered a numerator into the denominator. Now a to the power of positive 20. But again, we need something in that place value for the numerator, so I'll just put a phantom 1 there. Now, some of you may be able to work much faster than that. In fact, you probably wouldn't even need to show all that work, but I'm showing more work perhaps than is needed so that some of you that are still struggling a little bit with this can understand it just a little bit better. There's the rule. Again, it may be better to show that as over 1 so that you know you're flipping this from a numerator to a denominator. The base goes from numerator to denominator, which changes the sign of the exponent. So yeah, we see that word again, reciprocate. It just means we're going to reciprocate the base while changing the sign of the exponent. All right, lots of examples here, but I think this should go pretty quick because, once again, we're just reciprocating stuff with negative exponents. So that'd be 4, sorry, you need to change this into the denominator, right? So now it's 4 to the power of 1. And yeah, you can show a phantom 1 there. In fact, I'm going to make the exponent a phantom 1. Just make that 1/4. But I also feel like I'm going fast. So again, I'd show that as x to the power of negative 2 over 1. I just want that base flip from the numerator to the denominator. Now the exponent's positive, so x to the power of 2. Yeah, we'll show the phantom 1 there. So on this one, again, I'm going to show these as in the numerator. Now you don't see that divide by 1. That's a phantom divide by 1, which is the identity property for division. So just understand that if you don't see a denominator, you have one, it's just you don't see it. So you may want to show it if it helps you. So I'm going to start with the base x. So see how it's a negative 3, but it's in the numerator. I'm going to flip it to the denominator, which makes the exponent positive. Same with my base y. It's in the numerator, but I'm going to flip it to the denominator, which is going to change the sign of the exponent from negative 4 to positive 4. Then again, I'll show a phantom 1 in that numerator. Now be careful on problems like this because we're going to still show it as a fraction because we do have that negative exponent, but we only flip the bases that have negative exponents. In this case, it's base a. So where we have that negative 3 exponent and it's in the numerator, I change it to the denominator, which changes the sign of the exponent. But the b to the power 4 is already has a positive exponent, so I'm just going to keep it b to the power 4 in the numerator. So be careful on that one because sometimes we get so used to just flipping stuff. It's like we're going to flip everything, and it's like, well, you didn't have to. We want positive exponents. This one's already positive exponent. Keep it the way it is. Like on this one here, we got a to the power of negative 5. Now that's a to the power of negative 5 in the denominator. We can show a fraction just so we know we're flipping it. And now it's a to the power of 5, but now in the numerator. And yet that'd be a divide by 1. So I'm just going to make it a phantom divide by 1 so it looks a little bit more pretty, a little bit more clean, I guess. And then f, yeah, so again, we see multiple bases being operated on this. In fact, let's just focus on one base at a time. So I'm going to start with base a. So I can't ignore the other bases for now because we're just dealing with straight multiplication on this one. The base a has exponents of 2 and 3, 2 in the numerator, 3 in the denominator. It's all being divided, so I am subtracting this, the exponents. So now I have base a, but now it's to the power of 2 minus 3, which is negative 1. Well, I should give myself some more space there. I'm going to show that as a fraction because now I'm going to flip it. And yeah, that'd be over 1, but to flip that then it would be a to the power of 1. But the sign of that exponent changed from negative to positive there. So since it's a power of 1, though, I'm going to make it a phantom 1. Just looks more pretty. So now my base a has an exponent of a positive 1, phantom 1, and that's as far as I need to take this. But then I need to focus on base b, right? And be careful on the base b's because that exponent of the numerator there's positive 1. It's a phantom 1 exponent. So we're going to take that 1. We're going to subtract because it's being divided the exponent from the denominator for base b, which is negative 4. And yeah, that's 1 minus negative 4, which if you put into the calculator would tell you it's b to the power of positive 5. So that b to the power of 5 is just going to stay in the numerator. It's b to the power of positive 5 because the exponent was already positive. Now, the c to the power of negative 3 here, it has a negative exponent. It's in the numerator, so I'm just going to move it directly into the denominator, which changes the sign of its exponent. So if we write this throughout with the rest of our work, we end up with something like this. But right here at the end, again, this is what we're looking for, because for the most part in the assignment, it's just going to want these positive exponents like this. All right, G. We're going to start with just focusing on the different kinds of bases. And right here I see 4 times 3. And I know, and I hope everyone else knows, that 4 times 3 is 12. So I'm going to write that as 12, by the way, and that's okay. But then I'm going to focus on my base n's. And right here it has an exponent of negative 2. Here it has an exponent of 3. But since we're using multiplication between everything, we're going to be adding those exponents. So we see a little bit of a mixture of the properties and principles with exponents that we've been dealing with. And this would end up being n to the power of negative 2 plus 3. I get 1. So in my answer, you could put n to the power of 1, but again, just especially doing it by hand, we would just want it like this. So that's just 12n. It's good. All right, in part H, two different bases. We got base m. In the numerator, we have exponent of 5. In the denominator, exponent of 2. And yes, we are dividing, so we're going to subtract now those exponents, which would end up being m to the power of 5 minus 2, which is 3. So right off the bat, I get m to the power of 3, and I've kind of offset that hopefully a little bit higher so that if we need a denominator, we can keep it higher for the numerator. So the base n, once again, it has an exponent of 1 for that numerator right there, so that's 1. We are dividing, so we're going to subtract the denominator for the exponent for the denominator, which is 3. And sure enough, this comes out as n to the power of negative 2. 1 minus 3 is negative 2. So again, I'm showing more work perhaps than everyone would need, but some of you, hopefully it helps. And I'll show this as over 1, m to the power of 3 times n to the power of negative 2 over 1 because of the negative exponent, which I now need to flip. So that n to the power of negative 2 will be in the denominator as n to the power of positive 2 because it flipped. And the m to the power of 3 will just stay in the numerator as it was. And that is done. So part I, this is base m. We're going to take those two exponents, negative 3 and the 2. But since these are separated by parentheses like this, that's when we multiply the exponents. This ends up being m to the power of negative 3 times 2. I get negative 6. But again, we'll show that as a fraction because of the negative exponent so that we can flip it. So that it becomes m to the power of 6, but a 1 in the numerator. So I would say this is our final answer on this one. Simplify these in order from least to greatest. It's not too bad. So right here, I see something to the power of 0 is just 1. I'm showing their actual values, then we'll put them in their original values in the end here, okay? Now, I'm too lazy to do 6 to the power of 4, so I'm going to use the calculator. 6 to the power of 4. Just up here at the top, I'll make a note that 6 to the power of 4 is 1,296. Now, knowing that, I can figure out all these values because just based on how many negatives there are. So on this one, the exponent's 4, the base is negative in parentheses, so that's 4 negatives. 4 is even, so my answer is positive. So this one would come out as 1,296. We already know negative 6 to the power of 0 is 1. Now, just in case you were wondering, if this did not have parentheses, it would still be a negative 1 because it's only one negative. Just like on this example, there are no parentheses. So even though the base is to the power of 4, again, by the order of operations, there's only one negative. One is odd, which makes this a negative answer. Negative 1,296. But on this one right here, negative 6 in parentheses to the power of negative 4. Again, you can show that over 1. I would have to flip it to make it 1 over 6 to the power of 4. And we already know that 6 to the power of 4 is 1,296. So we get 1 over 1,296. This is a fractional value. It's just less than 1. It's not negative, though. That's important to know. So you could find the decimal value for this. What the heck, we'll figure it out. 1 divided by 1,296. I get 0.00077160, which is very small. It's very, very small. So to put these in order from least to greatest, the leastest would be the negative value. There's only one negative value. So that would be negative 6 to the power of 4. So we use that one up. Next up, we're in the positives, but the only fractional value I get there is the negative 6 in parentheses to the power of negative 4. So yeah, we use this one up too. Next up would be the value that was 1. That came from negative 6 in parentheses to the power of 0. And then we've only got one more value left, negative 6 to the power of 4. Boom. Let's list these all, 4 of them, in order from least to greatest. Yeah, sorry about that. I should have put this negative 6. Now, at this point, though, and this is, I think I did this in my mind a little bit too fast, but the negative 6 to the power of 4, we already know over here, because we've already evaluated that, is 1,296. That's because there's 4 negatives. So in my mind, I think I kind of skipped that step. I don't know. I think we've talked pretty extensively about this one. Number 3, though, this is a good one. So on number 3, we get 6 times t to the power of negative 2, and in parentheses, 6t to the power of negative 2. Remember that on this one right here, the 6 actually has an exponent of positive 1, where it's just the base t that has the exponent of negative 2. Now, if they're both in parentheses, then yes, the negative 2 would apply to both, which is going to flip both. Now, you could say it would flip the parentheses, and that would be okay. And then you could apply the exponent by multiplying it by the exponents on the inside, and that would be fine. But yeah, on this first one, you're going to end up with something like this, 6 over t to the power of 2. On the second one, you end up with 1 over 36 times t to the power of 2, because the 6 was also to the power of 2. Be very careful on that stuff. Up here, yeah, this one's just saying, here you got 1 negative, but it's the base, and it's being multiplied by the base. On this one, you have a negative exponent, which means you're going to flip it. And on this one, you'd have a negative base in parentheses, which tells us we have 3 negatives. It's very different. And then there's this one. Let's see, what do we got? Oh, yeah, this one, again, that's 5 over 3, but it's the whole fraction to the power of negative 3. On this one, though, it's just the negative 3 is being applied only to the 5 base in the numerator. Very, very different on these ones. I don't know that like none of this is meant to like trick people up, but sometimes it does. So it's important to kind of notice these little differences on this stuff. All right, 5 to the power of negative 2 as a fraction. Boom, I did it. I suppose they may be going for something like this on this one. But usually, again, they want these written as with positive exponents like we did on this one. All right, x to the power of negative 6 is a fraction. You could just write it as a fraction like this. That would work. But again, if they want positive exponents, it'd be 1 over x to the power of positive 6. These are the same. These are the same. That's a negative right there. Boom. There's the objective. I can find, simplify, and evaluate negative and 0 exponents. See how fun that was?